Hi everybody. Here we are. We're going to start talking about what about if we have a weak acid or a weak base. And so up till now what we've talked about is how do we calculate the pH if we have a strong acid, how do we have calculate the pH if we have a strong base. From here on out we're going to spend some time talking about weak acids and bases. And so we're going to look into exactly how do we calculate the pH of weak acids and bases. And so one of the things that you are going to need to pay attention to is that when we have a weak acid, something like this, that is acetic acid, which can break apart into its hydrogen ions and its acetate ions, you'll find oftentimes that this has the double-headed arrow in it. The reason why it has the double-headed arrow is because it only partially dissociates, just like we learned about in the last unit. So whereas before we were talking about complete dissociation, now we're going to spend our time talking about partial dissociation, which means we're going to have an equilibrium situation, and that means that we are going to be discussing what to do to find out the pieces we need to maybe calculate Ka, maybe be able to calculate the hydrogen ion concentration, which is often termed as X, as you're going to see. So we're going to talk about the ins and outs of this and kind of get into it. So here we go. Our first example is a problem that says calculate the pH of a 1.00 times 10 to the negative 4 molarity solution of acetic acid, and the Ka of acetic acid is 1.8 times 10 to the negative 5. So there's your equation, and then that means that the Ka expression would be written as the concentration of H plus times the concentration of the acetate ion divided by the concentration of the entire original concentration of the acid. And so we're going to take a look at, well, what does that look like in terms of the Rice table? So as usual, the Rice table, we start with the reaction, and then we start with the initial concentrations, and then we show the change as in the molar change, so minus X on one side and plus X and plus X for the two species on the opposite side of the double-headed arrow. All right, so that means that we are going to have the equilibrium set up. At equilibrium, it's going to be 1.00 times 10 to the negative 4. And you will notice, as a part of this calculation, that we are going to make the minus X that you see in the denominator be treated as a negligible amount. That means we're going to ignore it as part of our calculation, and that is going to be always the way that you will handle this. Okay, so that means that our calculation is going to come out as 1.8 times 10 to the negative 5, that's a Ka, is approximately equal to X times X for the hydrogen ion concentration and the acetate ion concentration over the original concentration of 1.00 times 10 to the negative 4. So from this you can calculate what is X. And let's please remind you that what is X is also synonymous as in what is the hydrogen ion concentration. Now you might ask yourself, why is my X different than my original concentration? Well, it is because this is a weak acid. Weak acids only partially dissociate, so the X should be quite a bit less, and in fact it is over 10 times less than the original concentration of the acid. That means most of the acid has not dissociated. And there is a little bit of discussion here that you can read and write notes on about why we call this minus X part negligible. All right, what should you be doing with all of this information? As we are going through this video, you should be taking notes. If that means that you need to pause my talking so that you can take notes, this is going to be your only source of the notes. So you're going to want to pause my talking and take some notes. In fact, I am going to make the notes that you take part of your assignment for this week. So please be prepared for whatever you write to be able to post a picture of the note-taking that you did. So let's continue on. If you need to pause me at any time, please pause me. All right. So we are going to move on to page 2. And in page 2, we have an example problem. And here is our first exercise. There's a lot of discussion here. It talks about the hypochlorite ion and what the active ingredient in swimming pool water is. But mainly it's what you need to know comes from right here. The hypochlorite ion has a relatively high affinity for protons and forms the weakly acidic hypochloric acid. So then the question is, calculate the pH of a 0.100 molar aqueous solution of hypochlorous acid. And of course it gives us the Ka value of that hypochlorous acid. So first thing we're going to want to do is we're going to want to write the dissociation equation, and I wrote it out so that you can see the actual movement of the hydrogen ion from the hypochlorous acid to the water, making the hydronium ion and leaving behind the OCl1- as the conjugate base of the hypochlorous acid. So then we move on to the initial concentrations, which was 0.100 and 0 and 0 on the product side. And then we're again going to have minus x and plus x and plus x. Here is going to be the interesting part of this. This change for the weak acid, weak base calculations is always going to look the same. Previously, when we did equilibrium, the change changed based on what the coefficients were. Now, since our coefficients of the acid dissociations are always going to be 1, we will not ever use anything but minus x and plus x and plus x. Okay. Once again, we have our then equilibrium, and from the equation, we can write our Ka expression, and I went ahead and pointed some arrows to you so you would know what everything looks like. Then we're going to plug in our values. So you see me plugging in the values here, and you see me negating the x, so you can tell, aha, that is not needed in my calculation. And then we can go ahead and solve for what is the final outcome. In other words, what is the concentration of the hydronium ion, which please remember that's the same as saying what is the concentration of the hydrogen ion. And then we can plug that into our pH calculation to calculate the pH. Now, you might notice that I wrote down 2 decimals underneath here, and that is because going back to our original concentration, we noticed that the original concentration had in it three significant figures. I was looking at this concentration. That means my 3 significant figures from 0.100. Mrs. Sher made a mistake. 0.100 is 3 significant figures. That means our decimal places here should have been 3 significant figures as well. So keep that in mind when you're doing these. The number of significant figures in the original concentration should be equal to the number of decimal places in the outcome or the pH. All right, so one example of me doing something just a little bit incorrectly there. All right, so then we go on to the next one. What if we have more than one Ka value in a mixture of acids? Then we usually just use the largest one, simply because it is the one that is far more powerful than the rest of them. All right, so we go on to another type of calculation, and that is what if we need to calculate the percent dissociation. This is what percent is our acid breaking apart into its ions. So we're going to use the format, and the format is written right up here, is the percent dissociation is equal to X, in other words, the hydrogen ion concentration, over the original concentration times 100. And I did that for A and B in this problem here. So my percent dissociation, I have the dissociation equation, I have the original concentration, I have the change in those concentrations, and then I have the equilibrium value. So I write my Ka expression, and I go ahead and I plug my numbers in, and I'm able to then solve for what is X. In this case, 0.00424, which is 3 significant figures. Now, the Ka is the same for B as it is for A, so I'm going to plug the same things in. The only difference is that I will use a different concentration for the original concentration, and I will go ahead and solve for X in those cases. So what are my percents? My percent in A comes out to 0.424%, which truly is a very small percent of dissociation, and my percent dissociation in B is 1.34%, also very small. So the idea is that, in fact, we understand weak acids only partially dissociate. If you need to stop the video right now so you can get some writing done, please do that. If you need to go back to get some more writing done, remember, you are taking notes of all of this. My intent is that, yes, you are writing everything down. Okay. Now, at this point in time, you should pause and try to see if you can work out this problem. This problem says lactic acid is a waste product that accumulates in muscle tissue during exertion, leading to pain and a feeling of fatigue. In a 0.100 molar aqueous solution, lactic acid is 3.7% dissociated. Calculate the value for Ka for this acid. Please pause right now so that you can calculate what you think the answer should be, and then I will come back on and we will continue on with what the answer does come out to. Okay, after you have paused and you have your answer, let's scroll down to how should this have worked out. In this example, we were using percent dissociation, and we were trying to see what we would be able to solve for. And in fact, we were solving for the X, what is the hydrogen ion concentration. So we have our percent dissociation, 3.8. We have our initial concentration of 0.100 times 100. And so to solve for X, I'm going to end up as dividing by 100 on both sides and multiplying by 0.100 on both sides. So that gives me X is equal to 0.0037 molar. Now, that's all great, and we can report then what the Ka value is by remembering the Ka expression, which is X squared over the original concentration, and when I do that, I get 1.4 times 10 to the negative 4. If the problem had also asked you for the pH, then at this time you would have been able to plug in your hydrogen ion concentration, and you would have been able to get your pH by using negative log of the hydrogen ion concentration. All right, so that is percent dissociation. Now, up to this point, we've talked about, well, we have a weak acid, here's what we do. What about if we have a weak base? So let's take a look at a couple of examples of what about if we have weak bases. So here we go. We are going to calculate the pH for a 15.0 molar solution of NH3, and the Kb for NH3 is 1.8 times 10 to the negative 5. Did you notice I said Kb? That is because this is the base dissociation constant, not the acid dissociation constant. Okay, so we have to write out first our dissociation equation. And you might as well go ahead and memorize this equation, because this equation is so well used and often used by IB that you might as well have this equation memorized. All right, so our initial concentrations are 15.0, 0 minus X plus X, and then we're going to plug in our values for equilibrium using our base, our Kb expression, plugging in our numbers. We're able to solve for, in this case, X is the hydroxide ion concentration, and then we're going to plug that into the negative log of hydroxide, giving us POH, and subtract it from pH, giving us the pH of the value. Now, here's another situation where you will pause your video right now. I'm going to go ahead and scroll this down so you can see the question that we're pausing on. This is your job to now see if you can answer the question. Calculate the pH of a 1.0 molar solution of methylamine, CH3, NH2, with a Kb equals 4.38 times 10 to the negative 4. Go ahead and take this time right now, pause, and answer this question. Okay, so after we have answered our own answer, let's see if we did it, okay? We also had to write out the base